Hey y'all, welcome back to my channel. My name is Jeffrey. In this video, I'm going to describe pharmacodynamics. Now, this is going to contrast with pharmacokinetics. Kinetics is about how fast your body metabolizes a drug and eliminates it from your body, your system, right? Pharmacodynamics is going to be talking about the effect that your drug has on your body itself. So the binding and the downstream effects on your cells. Okay, so there's going to be several different drug targets, and these are going to be the most common ones. The first is going to be ion channels. It could be your sodium, potassium, chloride channels. GPCRs, which is going to be the majority of prescription drugs today. And the reason why we target GPCRs is because one molecule can lead to a variety of effects because of that those downstream effectors of GPCRs, the signal cascade, right? And then we have your enzyme-linked receptors, and the most common is going to be receptor tyrosine kinases. So, for example, if you have type 1 diabetes, you're going to be prescribed insulin, and when you take insulin, it's going to bind to these receptor tyrosine kinases. It's going to trigger a downstream cascade, leading to GLUT4 receptors going into the plasma membrane, allowing for glucose to go into the cell and out of your bloodstream. You have nuclear receptors, so those include your nonpolar compounds, your steroid, thyroid, vitamin D, and these are just going to diffuse across your cell membrane, and they're going to bind to certain nuclear receptors affecting transcription. They act as transcription factors. Okay, you have enzymes, and for drugs, typically what we do is we try to inhibit these enzymes. So we bind to their active site, we bind to allosteric sites to inhibit the function of these enzymes. We have transporters. These could be these are usually neurotransmitter transporters. So serotonin, acetylcholine, stuff like that. And then you have structural proteins, and these are going to be anti-cancer. So, for example, tubulin. You can have certain drugs that are going to be toxins for tubulin, allowing for either the locking of tubulin or being unable to depolymerize. Okay, so moving to the dose response curve here. Um, uh, Basically, these are going to be going to be graded responses, and what that means is that response can increase and it can decrease with every little dose of the drug, right? And then, so this is going to be E is going to represent your effect. E max is going to represent the concentration at which you're going to have your max effect on your body, on your cell. EC50 is going to be the concentration that you're going to have the the concentration for half effect, right? And the C is going to be the concentration of your drug. For your receptor binding, you're going to have that B, and B just represents how many receptors are bound. And it's going to be a B max, which is going to be the maximum amount of receptors that you're going to bind. And C is going to represent the concentration. KD represents the dissociation constant, which means essentially just when your drug binds to its receptor, how long does it take for it to disassociate from that receptor to fall off? Right? So if you have a higher KD, it'll be more likely to fall off. And if you have a lower KD, it'll be less likely to fall. Okay? So we can kind of see that process over here on the right-hand graph. And this is just going to uh, allow you to take a look at that EC50, which is that potential to reach half effect, versus that KD graph that we were talking about before. And as you can see, you don't have to have they're not exactly the same, which suggests that you don't need to have um, maximum binding of the receptors to achieve your a full response from your cell. So we can see from the right here, I said agonist does not have to occupy every single receptor on a cell to evoke a full response from that cell. Okay, so my pointer is not working right now, so unfortunately I will not be able to point along with you guys. But um, we're just going to talk about agonists and antagonists real quick. So agonists are going to have an affinity for that active site of an enzyme or the affinity for the receptor that it's going to bind to, and it's going to have high efficacy. That means that it causes an effect, right? Antagonists have a high affinity for that site, but they actually don't cause a downstream effect. So if we take a look, if we remember from that receptor tyrosine kinase, if you bind to that receptor tyrosine kinase, it's going to phosphorylate downstream effectors, and as a result, you're going to have GLUT receptors. So what that is if you have a drug that mimics that the ligand that binds to the receptor, it's going to be an agonist, right? And then there's some receptors where if you bind to them, it's not actually going to cause an effect. Maybe it's not the correct ligand, but it still binds, or maybe it's a constitutive pathway, and binding of an antagonist actually stops that pathway. Okay, so um, you have reversible competitive antagonists here on in blue, and you can see that essentially if you're and we're looking at the EC50 of these curves, okay? So essentially, if you have an agonist with a reversible competitive antagonist, it's going to move that curve to the right. And what that means is that it actually is harder to achieve that therapeutic effect of having that EC50 closer to zero, right? And if you think about it, it makes sense because if you have a reversible competitive antagonist and the antagonist doesn't do anything, and it's competitively trying to butt into that active site or that receptor against the actual agonist that you need, then obviously that curve is going to shift to the right, right? And then for your irreversible competitive antagonists and your non-competitive antagonists, they're essentially going to be the same thing. So you might have learned these as suicidal inhibitors when you were looking at enzymes. And essentially what it does is that it binds covalently to that receptor. It binds covalently to the active site, right? So what happens is obviously you're going to have a decrease in the total efficacy of your agonist, right? So you're going to have a different slope. You're not going to reach that same very high EC50 that you might have had before. And then if we're looking at non-receptor, which means that the drug just the drug opposes the effect of maybe another drug or a constitutive pathway. So if we're looking at epinephrine and histamine, epinephrine is going to vasodilate and it's going to increase blood pressure, and histamine is actually going to vasoconstrict or decrease your blood pressure, right? So these two work in concert and they are opposites of each other, right? So if we take a look, oh, I don't actually have a graph for that one, sorry. And then if you, moving down, for full agonists, that achieves the maximum response that we were talking about before. And then partial agonists, it's a sub-maximal response. So if we take a look at the graph, it's going to be kind of similar to both of the graphs that we were looking at before. So in white, you can see the full agonist, it reaches its full potential. And then for the partial agonist, you can see that it only reaches maybe half or maybe three quarters. But either it doesn't matter what percentage it is, it's still going to be lower than that full agonist, right? But if you combine the two, it actually kind of looks like that competitive antagonist with full agonist from before. And it's essentially, if you think about it, it makes sense because partial agonists are going to act kind of like a reversible competitive antagonist, except that it's still going to elicit a response, but it'll elicit less of a response than a full agonist. So essentially, you're just going to have that same curve of the full agonist, but just shifted to the right, okay? And then you have these things called inverse agonists, which act on constitutive receptors that we talked about before. So, for example, some receptors are always going to be active, and maybe those result in continuous phosphorylation, and the binding of this inverse agonist is actually going to decrease the output of that constitutive receptor. Okay, so that's why it's negative from the zero line. All right, and then last but not least, we're going to talk about therapeutic index. This is basically where TD50 and LD50 just mean the toxic dose, right? So it means that at that dose, about half of the test animals, or maybe even half of humans, die at that dose, right? And then ED50 is going to be your maximum potency for that drug, or the most effective that it's going to be. So obviously, you want to strike a good balance between potentially killing your patient and reaching that therapeutic effect of what your drug is trying to do, right? So this is a measure of how safe a drug can be. And so, for example, if you had a drug and you know that the dosage of 50 milligrams is going to actually kill your patient, but you also know that anything less than 40 milligrams is going to be um, uh, it won't have an effect really on the disease that that patient has. So maybe you prescribe 45 milligrams and you keep, or maybe you prescribe even 30 milligrams and you keep cycling it through their system. So that's where pharmacokinetics is going to come in. Okay. Um, and then this final graph here is just a conglomeration of all of the different uh, combinations that you can have with full agonist, non-competitive antagonist, reversible competitive antagonists, um, uh, partial agonist, inverse agonist. So I hope that this has been helpful. I hope that pharmacodynamics doesn't sound as tough as it did before. Thank you. Have a great day.